Hello everyone. In this video we will talk about lenses. A lot of the discussion will be similar to what we had already discussed for mirrors. So for instance, we will start by talking about rays that are called paraxial rays, if folks remember what paraxial rays were. So paraxial rays are often those rays that are close to the mirror or close to the principal axis of the mirror, right? In this particular case, since we are talking about lenses, so this is also going to be close to the principal axis of the lens, right? And since we are going to deal with only rays that are close to the principal axis of the lens, that means we can treat the lens as a thin lens. So we are only going to focus on thin lenses. And since we are going to talk about thin lenses only, again, I can represent the lens by this line. And then the axis of the lens would be this line that is perpendicular to the lens. Okay, and now where the axis meets the lens, we will call that point the optical center of the lens, optical center. Now, if you remember, the curved mirrors had a focus and a center of curvature. So similarly, lenses, because these are curved as well, will have a focus and a center of curvature. Now, the kind of lenses that we are going to talk about will have a focus and a center of curvature on both of their sides. So this will be the focus, let's say, and this would be the center of curvature, and there will be one of each on the left side as well as the right side of the lens. So focal point or focus, okay, either way is correct, and the other point is center of curvature. Okay, so essentially we are dealing with objects that are either biconcave or biconvex. Okay, so if I were to sort of try to draw this straight line into an actual lens, then the biconcave lens would look something like this, concave on both sides. So this is concave on both sides. Okay, and then biconvex would look something like this, right? So this is convex on both sides. Okay. All right, so that's biconvex or biconcave lenses, and so they will have a focal point and a center of curvature, again, on both sides. And the focal length, so this distance from the optical center to the focal point, we'll call that the focal length F. So there's going to be a focal length on both sides of the lens. And the distance from the optical center to the center of curvature, we'll call that R, or radius of curvature. Right, so let's write these down. R equals radius of curvature, and these quantities, radius of curvature and focal length, these were there even for the case of mirrors, right? We talked about focal length and radius of curvature of a curved mirror. So similarly, that's going to be true for lenses. The only additional thing is that lenses will have the kind of lenses we are going to talk about, they will have a focal length and a radius of curvature on both sides. Okay, and the relationship between R and F is stays the same. So R is equal to 2 times F. Okay, so this is going to be true for our case as well. All right, and the other idea is that concave lenses, these kind of lenses are going to be diverging lenses. Okay, and convex lenses, these are going to be converging lenses. Okay, so these are converging, the other ones are diverging lenses. Okay, let's now talk about the basics of drawing ray diagrams. So basics of ray diagrams with lenses. So for the basics of ray diagrams, we'll start with a convex lens on this side, and then we will have a concave lens on this side. And whenever I talk about convex or concave, I'm really talking about a diverging lens and a converging lens. These are both thin lenses, and since these are thin lenses, I can just draw a straight line to represent the thin lens, and then the principal axis will just be a line, a dashed line perpendicular to the lens, drawn like that, right? So the first ray example that we will give is a parallel ray. So this is a ray of light that comes in parallel to the principal axis of the lens, and after refraction from a convex or converging lens, it reaches or passes through the focus of the lens. Okay, passes straight through the focus of the lens. This is an example of a parallel ray going through a converging lens. So parallel ray, right? Okay, now what would happen if the ray came to a diverging or a concave lens? Well, since this is a diverging lens, you can see after refraction from the lens, this ray should diverge, so it should go away from the principal axis, right? So that's what's going to happen, but it's going to appear. The rule is that if a ray of light is parallel originally to the principal axis, and after refraction, it will appear to be coming from the focus on the other side. So the focus on the side of the ray of the incident ray, right? So this is the focus on the side of the refracted ray, and that's the focus on the side of the incident ray. These are how these two differ. And in both cases, we have just drawn the parallel ray. So now you can tell quite easily that for a convex lens, the focus is going to be focus on refracted side and focus on refracted side, while for a concave lens or a diverging lens, focus on incident side. And this is kind of an important distinction. Okay, so when we start doing our mathematics with lenses, you will see we will talk about the incident side, and we'll talk about the refracted side. Okay, and when we talk about objects and images, object will be positive over here, so object distance will be positive here, object distance positive here, negative here, right? So this is the lens, and image distance will behave just exactly the opposite, so image distance will be negative here, positive here. So you can tell then the focal length for a convex lens is focal length is positive, focal length equals plus, and on the other hand, for a converging or for a diverging lens, the opposite thing happens, whereas this convention still stays the same, but now the focal length is on the object side, so the focal length is really negative. Okay, we'll come back to this in a second and talk about this in a little more detail, but let's talk about a couple of other ways that rays of light can go through a lens. So the second example would be if a ray of light is incident at the optical center, then it passes undeviated. So if I have a ray of light that comes like that, then that goes undeviated. And the same exact thing is true even for diverging lenses. This is not different. If a ray of light comes through the optical center, it just passes undeviated. Okay, now let's talk about the third kind of ray, which is a ray of light if it's coming from the focus. So if a ray of light is coming from the focus after refraction, it will become parallel to the principal axis in the case of a convex or converging lens. And in the case of a diverging lens, a ray of light that was appearing to go toward the opposite focus after refraction will become parallel to the principal axis. Okay, so that's the idea. So those are mainly the three kinds of rays that we will have to deal with for drawing ray diagrams. All right, the next part is to talk about the different formulae that we can use to solve problems. So particularly for lenses, we already mentioned the formula 2 times f is equal to r, or r equals 2f, or if you want, f is equal to r over 2. Sometimes this is useful. And the second formula that we have already encountered for mirrors is going to be the same for lenses as well. It's 1 over f is equal to 1 over s plus 1 over s prime. So what do these refer to? Well, f refers to the focal length of the lens, as you know, and s refers to the object distance, okay, and s prime refers to the image distance. Now, in order to do math with this, we'll have to remember the convention. So the convention is that if this is the object side of the lens, right? So this is the object side of the lens, and this is the image side of the lens. Okay, once the object side is known, the other side has to be image side, and this straight line is the thin lens in the middle, right? Then what happens is over here on this side, object distance is positive. Object distance is positive. Okay, but image distance, if the image falls on this side, then the image distance is negative. Okay, all right. And on this side, image distance, on the image side, image distance is positive. Okay, but object distance is negative. Okay, and now for various scenarios, we can actually play with the scenarios as to what happens. So let's say let's do the first situation where my object is at focus. So object at focus for converging lens. Okay. Okay, so then that means that this is my picture, this is my lens, this is my dashed line for the principal axis, this is the focus. So as you can tell that this ray of light after refraction, it's going to go through the other focus on the other side like this, right? And then we'll have a second ray of light that will go straight through the center of the optical center of the lens, and it's going to go like that. So these two rays after refraction will become parallel, so my image will be formed at infinity. Okay, how do we see this in math? Well, my object distance, this is my S, but this is also the focus, right? So that's the focus. So if that's the focus, this is also equal to F. So now let's plug it in. 1 over F equals 1 over S plus 1 over S prime with S equal to F. So this is only possible if 1 over F equals 1 over F plus 1 over S prime, which means S prime is equal to infinity. Okay, or you can say undefined if you like it, if you like that. All right, and how did that happen? Well, this 1 over F canceled, which means 1 over S prime ended up being equal to 0, and 0 over anything over 0. So S prime is 1 over 0, that would be infinite. And that's the idea. Okay, and we can also define another formula which will be important. We will call it magnification. It's the same exact thing as in mirrors. So M equals negative S prime over S. Okay, in this case, since S prime is infinite, magnification is also going to be infinite. All right, so now let's see what happens if you put the object at, instead of the focus, if you put it at, let's say, the center of curvature. So if I put the object at the center of curvature, we'll draw another figure over here. And so this is the focus, over here is the focus, and this is the center of curvature. So this is my object. And as you can see, if I have a parallel ray after it goes through the mirror, it's going to do that. Okay, and maybe I should draw this center of curvature part a little bit further away. Okay, somewhere over here. All right, and then if I have a second ray of light that goes through just the optical center, it's probably going to keep going like that and meet somewhere else. And just by knowing these 2 points, we can determine where this is going to be. Okay, and really, if you work it out properly with the math, you will see that actually also forms at the center of curvature. Okay, and we'll see that in just a second. So these are my 2 rays of light. And so as we can tell, this is the object distance, this is the focal length, F, and since this is the center of curvature, so if that is the center of curvature, you can tell that S is equal to 2F. So if S is equal to 2F, let's plug that into our formula. We have 1 over F is equal to 1 over s plus 1 over s prime, but this means that 1 over f is equal to 1 over 2 times f plus 1 over s prime. And so if I rewrite this formula, I'll get 1 over s prime is equal to 1 over f minus 1 over 2f, which is also equal to 1 over 2f. Okay, so s prime is equal to 2f. So s prime is equal to 2f. This is a positive s prime. So since it's a positive s prime, you see that this distance, which is the s prime, must be equal to 2f if s is equal to 2f. Okay, now let's try to calculate the magnification. M is equal to negative s prime over s, so we'll get negative 2f over 2f, which is negative 1. So what does that tell us? The magnification tells us that the object and the image have opposite sizes, right? So M is also, magnification is also equal to image size over object size. Okay, so since this is image size over object size, this is telling you that the image is inverted relative to the object. Okay, so these are a couple of examples of converging lenses. More detailed examples can be found by just working them out. So I have a sort of a display over here. Let me go to the display and we will see how we can manipulate the different sort of um, distances. So here is a video that you can actually play with, right? So when I put the object at the center of curvature, you see the image is formed at the center of curvature on the other side. This is for a converging lens. And as I move it backward further, the magnification becomes less than -1. It gets smaller and smaller as the object goes to infinity. If the object is far away at infinity, then the image is formed with 0 magnification at the focus. Okay, and then as I bring it closer and closer, at some point, this is equal in size but opposite in sign, so it's an inverted image. And then if I bring it closer further, at some point at the focus, it gets to infinite distance. And then as I bring it closer further, you can now see that the image has come to the same side as the object. So you see that the image distance is now negative. The object distance is still positive, but the image distance is negative. This is telling you that the magnification is now going to be positive and larger than 1, right? Because negative s prime over s is now greater than 1, or greater than 0 for sure, but also greater than 1 because s prime, negative s prime is greater than s, right? So this is telling you that the image is going to be magnified, and also since the image is forming on the same side as the mirror, as the lens itself, you can't really cast it on a screen because after refraction, all of the light goes to the other side, right? So this is a virtual image. All these other examples where I had moved the object sort of further out, these were all real images, but now as you get closer than the focus, you get a virtual magnified image. And this is an application of a convex lens to get a magnifying glass. So for a magnifying glass, if you hold the glass close enough to your object, then you see a virtual image which is magnified, which you cannot cast on a screen. That's the idea of a magnifying glass. So that's ray diagrams with convex lenses. With concave lenses, you can or the diverging lenses, you can do this, play a similar game, and you can move things around. But it turns out that your image will always be on the same side as the object. The image distance generally is always negative. As you move the object around, the image is formed between the focus and the optical center. Okay, so this is sort of the two kinds of lenses that we encounter. All right, so those are the two kinds of lenses. Now let's talk about what happens when we combine lenses, and in fact oftentimes we will need to combine lenses for optical instruments. Okay, so here is a good example of combination of lenses. So this particular picture, what is happening is I have 4 different rays of light. And you can see if this second lens, so there are 2 thin lenses here. This is a thin lens, and then this one is another thin lens. If this second thin lens was not there, if there was only the first thin lens, then these rays of light, after refraction from the first thin lens over here, will go and converge over there, right? So this is my virtual image of the first lens. So when I try to measure the object and image distances, what I'm going to do is I'm going to look at how far is the object from the first lens. So that's S1. That's the object distance here. And how far is the image from the first lens? So that's S1 prime. So the distance from this red arrow, dashed arrow, to the lens, that's S1 prime, right? Okay, so that's with just a single lens. Now what will happen when I have the second lens in the path? When the second lens is put in the path, then what's going to happen is that now the second lens is going to do its own bending of rays and form the final image over here. So when I try to now look at how to deal with this second lens, what I'm going to say is that the first image, the image that came from the first lens, is now the virtual object for the second lens. It's a virtual object for the second lens. Since this is the object distance will be counted from this arrow, from the red arrow, to the lens. And now notice that this object is on the refracted or the image side of the lens, which means this S2 here, that's going to be a negative quantity. Okay, S2 is a negative quantity. And S2 prime, which is now my final image distance, that's going to be, in this case, a positive quantity. All right. So we have S1, S1 prime, S2, and S2 prime, and then we can have a distance between the two lenses. Now the rest of it is just doing some algebra to figure out the different relationships. Let's particularly do this problem. So the problem has us set up such that two converging lenses each have focal length 10 centimeters are placed 15 centimeters apart, and an object is placed 15 centimeters away from the lens so that it is 30 centimeters away from the second lens. So let's go back to our canvas and we will do this problem. So we'll again, I don't want to do it with ray diagrams because the ray diagrams have already been drawn in that picture. We'll just try to do it with the focal length formula. So let's see. So this is my principal axis, and these two lenses, we know that they have been separated by 15 centimeters. So our D is equal to 15 centimeters here. All right, and then the original object has been placed somewhere over here at a distance of 15 centimeters away from the first lens. Okay, so S1 is equal to 15 centimeters, and F, let's call this F1, is equal to 10 centimeters. It turns out that F1 and F2 are the same. Okay, and F1 and F2 are both given and they're both 10 centimeters. Okay, so the focal length are both given, they're 10 centimeters. And since the focal length is positive, what kind of lens is this? Well, if it's a positive focal length, that has to be a converging lens. Okay, and in our case, it's generally a biconvex lens. All right, so now let's apply the formula 1 over F1 is equal to 1 over S1 plus 1 over S1 prime, right? Which will tell us that 1 over S1 prime is equal to 1 over F1 minus 1 over S1, which is equal to F1 times S1, and in the numerator it is S1 minus F1. All right, so S1 prime then is equal to S1 times F1 divided by S1 minus F1. And at this point, we can plug things in. So S1 is 15 and F1 is 10. 15 times 10 divided by 15 minus 10. And this is going to be in centimeters. Okay, so that's 150 divided by 5. 150 divided by 5, so that is equal to 30 centimeters. Okay, so that is 30 centimeters. So because S1 prime is 30 centimeters, that's going to be counted from the first lens. So it's 30 centimeters from the first lens. Okay, so if it's 30 centimeters from the first lens, how far is it from the second lens? Well, this is where the virtual object was formed. This distance is going to be 15 centimeters. All right, great. So that is 15 centimeters. Now, what is then the S2? Well, S2, you see, this is the object, this is the virtual object. It's behind the second lens. This is the first lens, this is the second lens. So S2 must be a negative quantity. S2 is negative 15 centimeters. Okay, S2 is negative 15 centimeters. Now our question is, what is S2 prime? As in, where does the second image, the final image, form. Okay, so because we also have to figure out sort of what kind of image it is, real or inverted, we should probably also think about at the beginning when we are doing this process, we should also think about the magnification. So in the first case, the magnification M1 was equal to negative S1 prime over S1, and you see that negative S1 prime is 30 centimeters divided by S1, which is 15 centimeters. This is going to give you negative 2, which means that this image is going to be twice as large, but it's going to be inverted, right? That's the idea of this M1 equals negative 2. Okay, so that's why this image over here, we didn't need to actually draw the ray diagrams to figure out that this was an inverted image, twice the size of the object. Okay, let's now try to find out S2 prime. So in order to find S2 prime, we will again use the same formula, except now ones will be replaced by twos. So I know that this same formula will apply, which means S2 prime will be equal to S2 times F2 divided by S2 minus F2. The only catch is that now S2 is a negative quantity. So let's put that back in. So this will tell us S2 prime is equal to S2 is negative 15 times F2. Okay, so F2 is 10 divided by S2 is negative 15 and F2 is 10. So negative 15, negative 10, and this is going to be in centimeters. So negative 150 divided by negative 25, you can see that the negatives here will cancel. So we are dealing with 150 divided by 25, which is equal to 6. Okay, so we'll get 6 centimeters. Okay, so S2 prime is 6 centimeters, S2 is negative 15 centimeters, then M2, which is equal to S2 prime over S2 with a negative sign in front, that's going to give us negative 6 over negative 15. So that's going to be positive 6 over 15 or positive 2 over 5. Okay, so positive 2 over 5, which is equal to 0.4. So since M2 is 0.4, we started with a virtual object that was inverted. Our result would also be an inverted object, which is smaller, 0.4 times as small as this. So since this is 0.4 times smaller than this is going to be somewhat like this. So this is my final image, and it's going to be 6 centimeters away in our second lens in this case, right? And we can also talk about an overall magnification. The overall magnification, M overall, will be equal to M1 multiplied by M2. In this case, that is equal to negative 2 multiplied by 0.4, so negative 0.8. Okay, so that tells, this overall magnification tells you that the original size of the object is larger than the image. The image is about 0.8 times the original object, and this negative sign tells you that the image is inverted relative to the object. Okay, so that's what we are seeing over here. If I go back to this point, then we are seeing that exact scenario over here. Okay, so this final image is formed at 6 centimeters away from the second lens, and it is smaller, slightly smaller than the original object. Okay, so that's the idea. This is how we work out problems with two lenses, and you can be asked the overall magnification, you can be asked all sorts of different questions about how far the object is or the images. So in this final stretch, I will talk about eye and corrective lenses. So the human eye sort of looks like this if you look at a cross section. There's the cornea, and then there's the pupil through which the rays of light can come into the eyes. And then there is the lens. This is the lens that we care about for our sort of lens-related questions. And the retina is the sort of the back surface of the eyeball. And the idea is that if you put an object in front of your eye, the rays of light will come through the pupil, get into the lens. The lens will adjust its focal length such that the image forms exactly on the retina. The retina is full of rods and cones, cells that are sensitive to light, and that then forms the image. The image sort of electrical pulses are transferred through the optic nerve to your brain. The brain then sort of tells you what this image looks like. Okay. The main features are that the lens, the eye lens, is primarily a converging lens, and it produces real and inverted images on the retina. Okay. And the eye lens can adjust the focal length. Its focal length is not a constant. It is adjusted through the contraction and relaxation of the ciliary muscles. These muscles over here, they when they stretch, when the muscles stretch, they actually pull the lens out. As it pulls the lens out, you can see that the lens becomes less bulging. And if these relax, then the lens becomes more bulging and hence more converging. Okay. So then the focal length increases as lens curvature increases, which means the ciliary muscles then contract. Okay, so that's the idea. Now, normally, so the normative eye, an eye that is sort of, I would say the standard normal, has what is called a near point closest to the eye that the eye can focus, equal to 25 centimeters. So if you put an object that is closer than 25 centimeters to the eye can't focus on it very well, which means that the ciliary muscles don't have the power of making the eye lens adjust to that focal length of 25 centimeters. And the normal eye far point, this is actually how far you can actually see with your eyes. Normally, this is infinite. Okay. Now, because of different kinds of disorders, neither the near point nor the far point have to be 25 centimeters or infinity. They can change, and we'll discuss how they change and how we can correct for them. So the first example would be a nearsighted example where a person is nearsighted, meaning they can't see things that are far away. Okay, so if it's a near object, then the eye, as long as it's away from the eye by at least 25 centimeters, the eye can still see it. But if the object is very far away, then the rays of light that are coming in, they because the eye has become over converging, the eye lens has become over converging, instead of having these rays of light go and form an image on the retina, what happens is the rays converge well before reaching the retina, which means by the time it reaches the retina, it looks like a blurred image. Okay, and how do you solve this problem? Well, if it's originally over converging, right? So if it's originally over converging, maybe we can make it so that it does not converge as much. So if you put a diverging lens in front, then what will happen is the rays of light that are coming from far away will first diverge, and as they diverge, now if you put the eye lens in front of that diverging rays, that will, with the over convergence, now converge on the retina, and the person will be able to see it. So that's nearsighted. The far-sighted example is just the opposite. So a far-sighted person can see very well far away, but they can't see things that are near, which means that their near point has now moved further away. So what happened with the nearsighted person is that their far point moved closer. For the far-sighted person, the near point moved further away. So what will happen is now the eye is under converging, and hence the after encountering the eye lens, these rays of light that were coming from a near point are now focusing somewhere behind the retina. So at the retina, it still looks like a blurry image, right? And so how do you fix it? Well, you put a converging lens in front. So if you put a converging lens in front, these seemingly divergent rays will now start slightly converging before reaching the eyes. And if they converge slightly before reaching the eye will then take care of the rest and make sure that the rays converge on the retina. Okay, so this sort of, I want to describe this in terms of diagrams, ray diagrams. So let's do that, right? So for ray diagrams, we will do the following. So instead of drawing these complicated eyeballs with all the structure of the eyeball and everything in here, what we're going to do is we're going to treat the eye lens as a thin lens, although it is not. Let's treat it as a thin lens, and then this is going to be my eye lens, and this is going to be my retina point, right? So some point on the retina here, and this is my eye lens. And then let's put in a principal axis. We'll put in a principal axis over there. Let's say that this is a nearsighted person, right? So nearsighted, since this person is nearsighted, they can't see far away well enough. Or the other way of talking about it is that they have a finite far point. So usually for a normal eye, the far point would be infinite. but they have a finite far point. So what's going on is rays of light which are coming in like this are now, they're coming in from infinity, would now converge before reaching the retina. So what could we do to combat this? Well, as we said, we could put in a diverging lens. So what would that diverging lens do? Well, what the diverging lens could do is, so this is still my eye lens, and I've put a diverging lens over here so that the rays of light, when they come in, the parallel rays of light that come in, will now diverge a little bit before reaching the eye lens. So this is still the eye lens. This is my corrective lens over here. Okay. So after interacting with the eye lens, now because these were a little more diverging, they will now converge on the retina. That's the idea, right? So this is still the retina. Okay. So what does this mean, right? What does this what is this corrective lens doing? Well, what it looks like it is doing is making it seem like after refraction, these rays of light are really coming from a different point, right? So as if the eye sees, although the actual object is at infinity, the eye sees these this as the object, right? As the virtual object. So this virtual object is really the image of, you can say, the virtual image due to the corrective lens. Okay, so which means now if I want to talk about image distance and object distance, I can just get away with saying that this is my image distance, S prime, and the object distance, of course, is, you know, wherever the object is relative to the eyeglass, the corrective lens, S. And then this will again satisfy 1 over F equals 1 over S plus 1 over S prime. Okay. For these kind of lenses, for corrective lenses, often the term that is also used is power of a lens. Power of a lens. And power of a lens is usually measured using a unit called diopter. Okay, so power of a lens is measured in diopters. Diopter. And what is a diopter? Well, 1 meter inverse is equal to 1 diopter, which means that that if I have a lens with focal length is equal to 1 meter, F equals 1 meter, then the power, by definition, power is 1 over F. That's equal to 1 over 1 meter, which is equal to 1 diopter. Okay, so that's the idea. Okay, and in here, if you want to do sort of the math for this, then what's happening is here that we want this S prime to be really the far point. So S prime is the far point for the bad or uncorrected eye, and S is the S is sort of the corrected far point or the normative far point, so S is infinite. Okay, so in this situation, what you want to do is you want S prime to be equal to F, because if S is infinite, you put that in, 1 over S becomes 0, so 1 over F equals 1 over S prime, so S prime is equal to F. Okay, so that's sort of the idea for these kind of problems. Sometimes it might be important to consider the distance between the eye lens and the corrective lens. Oftentimes, this far point for the bad or uncorrected eye would be measured from the far point itself would be measured. So far point measured from eye lens, not your corrective lens. And there might be some distance between the eye lens and the corrective lens. Let's call that D. So really the far point is instead of being S prime, the far point is S prime plus D. Okay, so the far point is S prime plus D, which means S prime is equal to far point minus D, kind of the idea. All right. So this is sort of the corrective lens usage for vision that is nearsighted or finite farpoint, and often also called myopic vision. And let's take the example of the other kind of vision, which is called hypermetropic vision. Okay, hypermetropia or farsighted hypermetropia or farsightedness. So what happens for a far-sighted person is that they can really see things that are far away pretty well. Okay, but they can't see things that are nearby very well. So for instance, over here, you could ask the question, what would have happened for a myopic person if my object was somewhere here? So that's not a problem, because if your object was somewhere over here, as long as it's within that far point, these rays of light, the eye lens can still sort of work well enough such that these two rays of light will converge appropriately at the retina. So that's the eye lens can still do that focusing. Okay, for a hypermetropic person, then the issue is with objects that are close by. So objects that are close by are not converging fast enough. Objects that are close by have diverging rays coming from them, and so they're not converging fast enough, meaning that they converge further out behind the retina. So if they converge behind the retina, again, you can't see them, or you will see them, but you will see sort of a blurry image over here, right? Because they're not converging properly. All right, so what do we do to fix it? Well, we want to put a lens in front of it, right? That's how we would do. So this is my eye lens, okay? And this is the retina. And let's say that this is the normative near point, okay? Normal near point. So if it's the normal near point, then this distance is just 25 centimeters. So this person whose eyes we are looking at, they can't see at 25 centimeters. They see blurry things at 25 centimeters, meaning that if I put something at the normal near point, it refracts and goes behind the retina. Okay, so what could we do? Well, let's put eyeglasses in front of the eye lens, and we'll still put the object at the normal near point. So now what will happen is, if you remember, these kind of rays, these kind of lenses are actually converging lenses. So this will make the rays converge a little bit. Okay, so as if now these rays are coming from further away. Okay, as long as these rays are coming from such far away that they are within the range where the eye can see, then these rays will again converge to a point on the retina. And that's the idea. So really what this corrective lens here, the corrective converging lens here, is doing is its image. So if this is the object, okay, so if that's the object, this is S. It's making sure that S prime is such that S prime is actually further back, right? S prime is behind the lens and it's further back. And as it is further back, it is making sure that this is the virtual object for the eye lens. And this point, that's the virtual object for the eye lens. And as long as this is really the actual near point of the person's eye, we are good to go. Okay, one catch for either of these kind of problems that we have to remember is that if you look at the first kind of problem here, S prime is behind the first lens, which means that this S prime here is negative, right? The object was in front of the lens, but the image is behind the lens. So here too, the object is in front of the lens, but the image is behind the lens. So again, S prime here is going to be negative. Okay. So as an example for the eye lens problems, we'll work out this the following problem. A person while wearing reading glasses that have a power equal to P1 equals 2 diopters can read at D1 equals 40 centimeters. Okay, so let's sort of draw the picture as to what's going on. So their glasses are placed 2 centimeters from their eyes, and they can read at 40 centimeters. Okay, and we are expected to find the location of the near point of their eyes. Okay, so if we place the object 40 centimeters from the eye, then the person can see it. So of course, this is going to be my first lens, corrective lens, and this is going to be my eye. So this is eye, corrective lens. And since this is the eye, that's the corrective lens, the distance between the two is equal to d. Okay, and that d is equal to, we know that d is equal to 2 centimeters. Okay, now the point is that at when the object is placed at 40 centimeters, they can actually read it. So if the object is placed over here at a distance d1, and since it doesn't say it clearly, we're just going to assume that d1 is from the eye. So d1, then they can properly read it, right? Which means that from here, whatever is going on, whatever convergence or whatever is happening, it's such that the rays of light, after refraction and everything, goes and reaches the retina. So I would think that this would be the picture and this would be the near point. We are interested in finding the near point of our eyes, so this is our near point. Okay, so this is our near point. Really what we are interested in is sort of this distance. Okay, this is our x that we are interested in. Okay, so d equals 2 centimeters. So now looking at this picture, we can tell for the corrective lens, the object distance, which is s, that is equal to, the object is in front of the lens, so that's a positive quantity. It's going to be equal to d1 minus d. And the focal length is, of course, given, right? So f1, we'll call that f1. Let's call this s1. s1 is equal to d1 minus d. f1 is equal to 1 over p1, which is equal to 1 over 2 diopters, which is equal to 0.5 over diopters, so 0.5 meter, which is also equal to 50 centimeters, right? So that's our focal length of the lens. And S1 is D1 minus D. We know D1 is 40 centimeters minus D, that is 38. D is 2 centimeters, so this is 38 centimeters. Okay, so that's the idea. And now we are expected to find X. But in this picture, if you look at the picture, then S1 prime is going to be equal to a negative quantity, right? Because it's formed behind the lens on the same side as the object. So S1 prime should be equal to negative x minus d. Okay? Or which is also equal to d minus x. So let's plug this into our focal length formula. So 1 over f1 is equal to 1 over s1 plus 1 over s1 prime. And if I plug that in, I have 1 over f1 is equal to 1 over s1 is 1 over d1 minus d plus 1 over s1 prime, so 1 over plus 1 over d minus x. Okay, so if I simplify this formula, it will look like 1 over d minus x is equal to 1 over f1 minus 1 over d1 minus d. And this becomes, if I just take the inverse of both sides, we can write d minus x is equal to f1 times d1 minus d divided by d1 minus d minus f1. And we eventually want to find x, which means x is equal to d minus f1 times d1 minus d divided by d1 minus d minus f1. And at this point, we can plug in all the numbers. D is 2 centimeters, so we'll get 2 minus, and I'm going to put these within brackets, 2 minus f1 is 50 centimeters, 50 times d1 minus d, that is 38 centimeters, divided by d1 minus d is 38 minus f1, which is 50 centimeters. And all of this should come out in centimeters. Okay. All right. So now if you do this calculation, you will find that this is equal to roughly 160 centimeters. And so that's the answer. So this is our person's near point for their eyes, right? For the uncorrected eyes. So now the second part of the question asks what power lens is needed to correct the. For this part, we now know the object and image distances. We just have to figure out the focal length. Okay, so how do we do that? So again, this time we'll call it S2. So S2 is equal to D2 minus DE. So in this case, D2, it tells us that that's 25 centimeters. So 25 minus D is still 2 centimeters. So this is 23 centimeters. Okay. And S2 prime, this is where we want the image to be formed. So S2 prime is just the same as this S1 prime was over here. So that's still negative x minus d, or is equal to d minus x, right? And so that we found that d minus x, so that's d was 2 centimeters, x is 160 centimeters. So this is roughly equal to negative 158 centimeters. All right, so the rest of this is going to be quite simple. So we are expected to find P2, the power of the lens, the corrective lens required, but P2 is equal to 1 over F2, which is equal to 1 over S2 plus 1 over S2 prime. And we can just simply substitute at this point. I would actually try to convert these to meters first to make life simple for us. So this is 0.23 meters. This is equal to negative 1.58 meters. And if I plug that in, then I get P2 is equal to 1 over 0.23 minus 1 over 1.58. And since these are already in meters, you would see that this is going to be equal to 3.71 over meter, which is equal to 3.71 diopters. So this is the new corrected correction of the vision will require this powered lens.